In this video, I will talk about the differential equation that describes simple harmonic motion and the solution to such a differential equation. So let's use the spring and mass system as our example. Okay, so the red line here represents the equilibrium position of the spring. And now if the spring is pulled to a new position x under such a coordinate system, and then let go, let's look at the Newton's second law for the mass m. So the free body diagram looks like this. There's a spring force pointing to the left, and the surface is smooth, so there's no friction in the horizontal direction. In the vertical direction, there's a normal force and there's a gravity. In the vertical direction, normal force and mg are balanced, and that contribution to net force will be 0. So the net force only comes from spring force. And in our coordinate system, the right side is positive. And according to Hooke's law, F spring equals negative kx. So the spring force is pointing to the left side, which is why there's a negative sign here. Now, according to Newton's second law, F net equals ma. And let's further write a here as the second derivative of the position vector with respect to time. We get negative kx equals m second derivative of x with respect to t. Okay. Now let's rewrite this equation to a so-called standard differential equation for simple harmonic motion. And let's divide by m on both sides, and let's move over k over m times x to the right side. We get second derivative of x with respect to t plus k over m times x equals 0. And let's replace k over m by omega squared. So omega equals square root k over m, which is defined as angular frequency of the simple harmonic motion. Now the solution of this differential equation is given by x equals a cosine omega t plus phi naught. A is the amplitude, so it depends on the initial condition. Let's say we pull the mass m from equilibrium position to a new position here, and then let go. Then this distance is the amplitude. That's the amplitude A. Okay, and omega already defined is the angular frequency. Now phi naught here also depends on initial condition. It actually is determined by the initial time when we start measuring the simple harmonic motion. So it's the initial condition. There's a separate video talking about how to determine the initial condition, how to use initial condition to determine the phi naught here. Okay, and phi naught is called phase constant. Okay. Now, this solution can be checked by taking second derivative with respect to t for the x, and then plug in this equation. So let's try this derivative. So the first derivative equals negative a sine negative omega a sine omega t plus y naught. And the second derivative is given by negative omega squared times a sine omega t plus y naught. And remember, a cosine, this one should be cosine. Remember, a cosine omega t is x. So we can rewrite this one as negative omega squared times x. Okay. So if you plug in the differential equation here, you get negative omega squared x plus omega squared x, which is of course 0. Okay. So we can check the solution in this form. And according to mathematical theory, differential equation theory, if you find a solution, then that is the only solution. Okay, so that's the only solution to this differential equation.